Good afternoon, everybody. My name is Yves Lambert. I'm Vice President of EVIA and also Chairman of the Ventilation Performance Assessment Tool. And as you can see, EVIA is the European Association for the Ventilation Industry, regrouping 45 members or companies in the residential and the non-residential ventilation area or manufacturers. Now, as the previous speakers have said, there is an interest in ranking the performance of ventilation systems. Now, next to that, there's also a commercial interest for ranking ventilation systems. There is already a ranking existing with eco-design, but that ranking is purely based on the energy efficiency. And as we all know, it's not the energy efficiency that counts in ventilation, it's mostly the performance on indoor air quality. So there's even a possibility that you have a very energy efficient ventilation system that has a poor performance on indoor air quality. So from a industry point of view, we wanted to do something about this labeling and wanted to add something to the energy efficiency. So the idea grew to be able to make a label similar to the energy efficiency label or the eco-design label and make one on indoor air quality. That was a bit easier said than done because, as you know, we have a lot of members and a lot of members with different interests. So the goal was easy to set, but to make it work and to develop everything as we wanted to develop it, it took us quite some time. If you look at the date, we started on March 5th, 2015. So it took us about 9 years to finish the tool we wanted to have. But anyway, it worked all out, and we did not do this by ourselves. We started off with a number of R&D people from the different manufacturers, and they all brought their own views to develop the tool. But after 1 or 2 years, we said, this is not going to work. We have too many different points of view. We need to have an external consultant helping us out. So we went to VHK, Van Holstein and Kemna, and asked them, can you help us build a methodology that kind of a common methodology that would bring all the different views of the manufacturers together? And that was Rob van Holstein and William Lee who accepted that challenge. But they did that together with Ghent University, with Professor Jelle Laverge, who then brought in the scientific part next to the consultant part, because we also needed information on scientific studies and field research to be able to check if the methodology that we were developing, if it will really work out and be consistent. Now, as it's written here, it's a methodology that assesses the actual occurring air exchange rates at room level type during presence and absence. So it has to, we want to determine if the ventilation system is able to remove or dilute pollutant where and when necessary. And because in most of the actual methodologies that are present in different member states, it's mostly only the air exchange rate that is looked upon, but not really the performance. So the idea was, can we develop this? At the end of the work, we have 2 big documents, which is on the one hand side, the left-hand side is the tool itself with the methodology, which is about 80 pages long. And we have a user manual specifically for our member companies who want to use the tool to be able to fill it out as they should do to get the label in the end. So also both of these documents were made together with VHK and University of Ghent. Now, the method itself, I think you will all be very familiar with the approach. We are looking at the different room types. So we are looking at habitable spaces, as we call them HS, habitable spaces, which are living rooms, bedrooms, study, and etc. We are looking at pollutants like bioeffluents, building material emissions, emissions from interior products, and pollutants from human activities like CO2. We look at an exposure during presence and an occupancy as long or very long, because, for instance, in bedrooms, you can spend more than 8 hours, so this occupancy time is much longer than in extract spaces. And for the reference ventilation strategy, we are looking at an air exchange during presence, but also during absence. And where we want to see is, can we supply sufficient fresh air in presence, and what are we going to do during absence? What kind of ventilation rates are required during absence to avoid accumulation of building our product emissions? That's for the habitable spaces. On the other hand, we have the extract spaces, where we look at pollutants like moisture or humidity, of course, odor, building material emissions, and emissions from human activities, exposure during presence, and then shorter occupancy time. And for the air exchange or the ventilation strategy, also during presence, for the extraction of sufficient air to get, for instance, to remove moisture or odor, for instance, in bathrooms or from showers. But also look at the air exchange during absence. How long is the humidity still present after somebody has taken a shower, and what is the amount of air that we need to extract to remove that? So we have habitable spaces and extract spaces. And then for the assessment method itself, we look at different system types. We call that VST, so ventilation system type, with their associated air exchange provisions in habitable spaces and extract spaces. We look at the type of fan, if it's a mechanical direct extract or mechanical direct supply fan, and what type of natural direct supply grids are used in the VST if it's a natural combination. What kind of airflow capacity is installed? What type of operation or controls? Are there any sensors used with the system? CO2 sensors, VOC sensors, humidity sensors, whatever. And what type of dwelling is it? How big is the dwelling? How many habitable spaces are there? How many extract spaces are there? What is the surface of that? And what is the air tightness of a dwelling? So we have quite a large number of variables that need to be entered to be able to calculate. There's an overview here of the different ventilation systems we have looked into. There were 7 determined, but we only evaluated 5 of them. The first 2 we left out because of budget limitations. The first one is a complete natural supply, and the second one is the overpressure system that is mostly used in the UK. But the other ones, the VST 3 until 7, are the UVUs or unidirectional ventilation units, which are completely what we call the standard systems or the demand control systems and the very complex demand control systems. And then the BVUs, the bidirectional ventilation units, the central ones, the simple ones, or the demand controlled ones. And then the 7 is the decentralized bidirectional ventilation units. So we have a complete overview of the systems that are mostly used in the European market. The assessment method looks in first place at the air exchange rate, where we look at the installed minimum and maximum ventilation capacity, both in extract and habitable spaces. And then we look at a probability that the installed ventilation capacity is actually achieved in those areas. We look at the same time what the driving force is it natural or mechanical? How many number and position are there of the doors, internal doors, because they can block or allow the air to pass. The air tightness of the dwelling, of course. Duct leakages of the systems, filter compensation for bidirectional ventilation units, internal leakage for bidirectional ventilation units, the airflow sensitivity, and the indoor-outdoor air tightness. So again, a large number of factors that need to be entered to be able to calculate the whole thing. From this, we calculate the probability that the controls that are integrated into the system or that are put into the system are in the right position to achieve the required ventilation airflow rate. For instance, if you're installing a CO2 sensor in a bathroom, that the probability that this sensor will achieve with the system a good indoor air quality is much less probable than if you install a good humidity sensor in that bathroom. For that, we use PCO values. PCO is then probability of correct operation. So also there, we had to determine a whole number of factors and discussed it with all the different manufacturers to see if we can all agree on the factors that were concluded and presented by VHK and University of Ghent. So for all the extract spaces and combined habitable spaces, the air exchange rate is calculated for periods of presence and for absence. From this air exchange rate, we move to an air exchange performance, which then compares to an air exchange reference. And for this reference, we use the EN 16798-1, and we chose to go for category 2 for a certain CO2 level into the buildings. And again, we calculate for the periods of presence and absence the air exchange performance. This is an overview of the Excel input sheet. So we have on the left-hand side at the top, you see a VST5, which is a BVU. With underneath that number 1 dwelling air tightness, so we can enter the air tightness of the specific building. We can enter underneath of that the number of exhaust and habitable spaces, and even determine what type of room it is. For instance, if it's an open kitchen or a closed kitchen, what are the habitable spaces and how many of there are there, and what is the size of those habitable spaces. Then the type of BVU, what type of fan is being used, what is the filter compensation. We can also specify the mechanical direct extract capacity, what is the maximum capacity, what is also the minimum capacity. If the system goes to a minimum level, what is that minimum level to guarantee indoor air quality. Same for mechanical direct supply capacity. And then we have to specify what type of control we are using in those exhaust and habitable spaces. As you can see under number 7, we see mechanical direct extract in the kitchen. There we can choose the control type, if it's relative humidity, local, zonal, or central. But it could also be CO2, it could also be VOC, it could also be a peer or whatever. So we have a large number of possibilities, and this allows us to enter a number of variables and see what is the result immediately. So if we change, for instance, the CO2, the relative humidity local in the bathroom, and we change that to CO2, we would see immediately that the end result would be less good than using that relative humidity. Also for habitable spaces, on the right-hand side, we can choose what type of controls we have in the habitable spaces, if there's a CO2 sensor or whatever. From all of these parameters, we get a result, and that result is a probability that the requested air exchange rate occurs in those individual spaces. As you can see, so below we can see open kitchen, bathroom, toilet, and then average extract spaces. We see a 98% probability that the requested air change is then achieved in those extract spaces. But for the habitable spaces, there's only 32% of an air exchange performance. So that's not so good. And that is mainly because there is no sensor in the habitable spaces that would control the indoor air quality there and increase the air supply if needed. So that's the general input sheet. Behind the input sheet, there's a big calculation sheet with all kinds of formulas that were discussed over the 9 years we worked on it. And there's also a number of lookup tables that have all the different factors that were decided during those 9 years of discussions. For instance, we are looking at reference values for occupancy in extract and habitable spaces. For instance, there's 1 kitchen, 1 bathroom, and a toilet. How much of the time are we in one of those rooms? So it's 9% of the day in kitchen, 4% in the bathroom, and 1% in the toilet, and so on, with a total occupation of extract spaces of 14%. And then on the other hand, we have a 63% of the day we are in habitable spaces. So that's the lookup tables. We have the inputs form, we have all the calculations, we get the result, and that's the design tool. Now, we are still a long way from design tool to a label, because the design tool allows you to calculate ventilation performance or air exchange performance for any size of dwelling, according to any kind of air exchange rate for national ventilation standards for your specific product. Now, to move to a label and be something that you can compare, we had to make a specific version for the calculation of the label. And for that, we needed a reference dwelling. So we had to change any size of dwelling to a specific European reference dwelling. All the national air exchange rates have to be changed to an EU air exchange rate. And then, of course, you can keep the ventilation unit product data to calculate this. To give you an example, the dwelling we decided upon as a fixed European dwelling, we took it from the building database. We chose that the dwelling surface was about 92 square meters. with about 66 square meters of habitable spaces, 3 exhaust spaces, and 3 habitable spaces with an air tightness of 2. So all these, well then, fixed. And as you can see here, we have the difference between both. We have the design tool and we have the label tool. The yellow cells are the ones you can enter. So we have a lot more yellow cells in the design tool than we have in the label tool. So this is the design tool. You can see you can change anything in the air tightness. You can change anything in the habitable and extract spaces. You can change BVU type. You can change the minimum and maximum capacities. You can change everything as far as controls is concerned. For the label tool, this is much more limited. So the reference dwelling limits does not allow you to change the number of rooms anymore, but you can still choose the type of the ventilation. You can no longer change the maximum capacity because that is limited to the 16798. And then we can still change the minimum capacity for the system and the type of controls. What we go very far in this, because sometimes we have new developments and we have to allow the tool to allow for innovation. So we are now looking at the development of zonal ventilation systems. And for instance, if you have a zonal system, you should be able to enter that your system is looking at, for controls in habitable spaces, you can only install CO2 sensor in a living room, or in master bedroom, or a combination of both, or all in every room. So in children's bedroom, master bedroom, and living room. And depending on those, the choice you've made for your ventilation system, you get a specific percentage. For instance, if you choose to only install it in the living room, you get a 60% control in the bedroom, or in the control for the habitable space. If you go beyond that, you can go to 85 or 100% if you have a CO2 sensor in all of the habitable spaces. So even for that, we checked this for the calculation. Now we have the design tool, we have the label tool. This has to be retranslated into a label design. So we had many different options with the marketing task force. So as you can see, many different ideas. The left one is more or less kind of a measles, so it's not very interesting because it more reflected something like some kind of sickness, but we didn't want that. The second one was too similar to the eco-design label, and then the other ones were not really clear what we wanted to have. We finally ended up with this one, which indicates the label itself, the manufacturer, the AEP score, the performance score for the extract spaces, and the performance score for habitable spaces, what type of sensors were being used, if it was local or zonal, whatever, and a filtration score. We thought we had it covered. We checked this with consumers, and then apparently they did not understand anything. So again, we were confronted with the fact that as ventilation professionals, we think very much that people will understand what we are talking about, but they did not understand anything. So we went back to the drawing board and redesigned the whole thing. And also we had to redesign the air exchange performance because we had 2 air exchange performance, one for the extract spaces and one for the habitable spaces. To make it simpler, we merged them with a weighting factor. This was also done with Ghent University and Van Hostein and Kemner together to have a merged AEP, which finally then allowed us to make a label. So for instance, if your merged AEP is at about 75%, you would end up in label B. If it's over 85%, you would have label A. This is then the final design after consulting with the consumers again. So we designed a kind of a house with an indicator of the label, with a little fan inside to show that it's a ventilation system, what types of sensors are being used, what type of airflow control, and what type of filtration. This is then for the members, the EVIA members, retranslated in a kind of a label generator. So if they have a system and they want to have it labeled, they have to just enter all the information they have here, and the generator will generate automatically the label. They can't do that immediately. The information has to be checked by Klaus Hendel, our technical secretary, before they can publish it. But this is now underway. Just to give you a few examples, this is a BVU with no sensors whatsoever. So as you can see in the middle, it's a class D. But the moment you add sensors, you get a class B. There's CO2 sensors and relative humidity sensors added, so we go to a class B. This is a VSD3 or a UVU. At the right-hand side, you can see its no control is label F, but the moment you add different controls, you have on the left-hand side relative humidity and a presence sensor, and it's a local sensor. Then you move also to a label B on indoor air quality or indoor air performance. And then last one is then a VSD7 or a decentralized BVU unit. On the left-hand side, there are no sensors included, so it's a label D, but the moment you add your sensors, you can even go to a label A. And that concludes my presentation. If there are any specific questions, the tool itself is limited to the EVIA members themselves. If anybody is interested, they can contact the Secretariat at EVIA under this following email address. Thank you for your attention.